Good morning, everyone. This is my last lecture for CHM 577, which is the recorded lecture number 17. And I'm going to talk about isomerism in coordination compounds. Thank you, Dr. Amalina, for preparing the notes. And I am presenting these notes with some additional items that I have put in the notes for my students. Now, everybody has heard about or has learned about isomerism, and everybody knows that isomers are compounds that have the same chemical formula, but they have different chemical and physical properties. For coordination compounds, the isomers can be broadly divided into two types, which are constitutional isomers or structural isomers, and the second one is stereoisomers. Constitutional isomers are further divided into two, which are coordination isomers and linkage isomers, whereas the stereoisomers are divided into another two, which are geometric isomers and optical isomers. Now, let me briefly go through the differences between these four different types of isomers. Okay, constitutional or structural isomers have atoms connected differently to the metals. And they can connect differently, atoms in the ligand, that is, atoms in the ligands connected differently to the metals. And these ligands can connect differently in the way of coordination isomers, where the ligand and the counter ion undergo exchange. You will see this clearly when I give you some examples in the next slide. And linkage isomers is when you have in the same ligand different donor atoms, and these different donor atoms are connecting to the metal separately. So I'm going to go through constitutional or structural isomers, differentiating between coordination isomers and linkage isomers. I'm going to go back to this page later for stereoisomers. Now, constitutional isomers have different connections among their constituent atoms. And the first type, which is the coordination isomers, or also sometimes called ionization isomers, differ in that the anion or the ligand is bonded to the metal center differently. So compare this compound. Yep. Can you see this compound? Where you have a cobalt, 5 ammonia, and 1 bromo, and 1 sulfate. In the first example, the bromo is acting as a ligand, whereas the sulfate is acting as a counter ion. And this being the case, you are going to have a violet coordination compound that has a bond between cobalt to the bromo ligand. That means your cobalt is accepting lone pair from the bromide, making a cobalt bromide dative covalent bond, and that's violet. But the same component or the same formula compound can behave differently, where in the second case, your sulfate is now being the ligand, whereas your bromide becoming the counter ion. So when your cobalt has a bond with your sulfate as a ligand and the bromide acting as a counter ion, you are going to get a red compound where you have cobalt datively bonded to the sulfate. So this formula and that formula, in terms of atoms, they are the same, but the connection is different. The first one has a connection cobalt to bromo, whereas the second one has a connection cobalt to sulfate for metal and ligand. So the first one has a violet color and the second one has a red color. So that is an example of coordination isomerism. Yeah? So these two are called coordination isomers. Clearly two different compounds, two different physical appearance, but they have the same formula, chemical formula. So that is clear. Coordination isomers, when they differ in that the anion is bonded differently to the metal center. Second is called the linkage isomers. It is when a ligand can bond through two different donor atoms. And this is, for example, NO2 or ONO. So this compound, the first compound that we have at the top here, the NO2 ligand is bonding the cobalt through nitrogen atom. And it gives you a yellow solid. You have cobalt that is bonded to N as a donor atom, giving you a yellow solid. But however, within NO2, your oxygen also has lone pair of electrons. And that oxygen can act as a donor atom. And when the donor atom is the oxygen, as is the case down here, the NO2 is now acting as ONO ligand. So your cobalt is bonded to oxygen rather than nitrogen. So in that case, you are going to get a red solid rather than a yellow solid. So your red solid is having a bond between the cobalt to O and O. I'm going to show you the picture in the next slide. Whereas your yellow solid is having a connection between the cobalt with nitrogen with two oxygen not bonded to the metal. So how is that possible? This is the photo, or this is the drawing, the chemical drawing of differently bonded NO2 in this case. This is your NO2 where the ligand is bonding through nitrogen and it is called a nitro ligand. And the second case where the same ligand is bonding through oxygen, in that case the ligand is called nitrito ligand. Not a nitro ligand, but a nitrito ligand. When the NO2 is bonding as a nitro, you get a yellow compound. When the NO2 is bonding as a nitrito, you get a red compound. So this is an example of linkage isomerism. Linkage isomerism is when the ligand has two different donor atoms and they bond differently in different situations. So those are linkage isomers. So I hope you understand the difference between coordination isomers, where the coordination occurs through different anions, and linkage isomers, where the coordination occurs through the same anion but on different atoms. Yeah, and these two types are called constitutional isomers, or sometimes some textbooks refer to them as structural isomers. So that's okay. That's not a big problem, or that's not very difficult to understand. Now, going back to this slide, the second type of isomerism that you might encounter in coordination compound is stereoisomers, where you have different arrangement in space, different spatial. Spatial means space, the situation in space, yeah? So what does it mean? You have the same formula compound, but those atoms or those ligands are differently arranged in space. So there are two types. One is geometric isomers, where you have cis isomer and trans isomer, and I think this is a little bit easier for you to understand. And the second type is called the optical isomers. Discussion on optical isomers is a little bit more involved, as you will see later. So we go to the easy one first. The geometric or the Cis Trans Isomers, they are called diastereomers. They have different arrangements around the metal atom, different arrangements of the same ligand around the metal atom. Whereas the optical isomers is when you have two compounds that are mirror images with each other, but they cannot be superimposed. Don't worry about this yet because I'm going to have a further discussion on this one in detail. So let's go to our geometric or cis trans isomers where they are diastereomers, having different arrangement around metal atoms. So let's go forward to this slide. So stereoisomers, the first type, stereoisomers generally are compounds that are made up of the same types and the same numbers of atoms, bonded together in the same sequence, but with different spatial arrangement, i.e. different arrangement in space. The first is your geometric isomers, Cistrans, where they are called diastereomers, and the second is the optical isomers, non-superimposable, where they're called Enantiomers. So let's go in detail about geometric isomers. Geometric isomers are stereoisomers that cannot be interconverted into each other without breaking any chemical bond. For example, you have the same formula, Pt, platinum, 2 ammonia, 2 chloro. The second one, platinum, 2 ammonia, 2 chloro. Now, when you have, we take chloro, for example, here. When you have the chloro situated next to each other or the same side in position, this isomer is called a cis isomer, same side. But when your chloro is located opposite or across of each other in that compound, then that isomer is called the trans isomer. So it's easy enough to understand. This is an example of a square planar compound where your chloro is on the same side for cis, your ammonia is on the same side for cis isomer, whereas your chloro are on the opposite side for trans, and your ammonia are also on the opposite side for this trans isomer. So it's quite easy for square planar, and it is also quite easy for I'll go to octahedral compound. Yeah, octahedral can also have cis in this situation where you have the same type of ligand next to each other in your octahedral compound, or you can also have trans where the same type of ligand, in this case chloro, they are across of each other in this compound. But I have skipped through two slides, which I don't want to do because I don't want to miss anything. So the geometric isomers or the stereoisomers have the same connections among atoms, but they have different spatial arrangements or spatial orientation of the metal ligand bond. The cis isomers have identical ligands on adjacent corners of a square or the same side, whereas the trans isomers have identical ligands across the corners, not adjacent. Adjacent is next to each other. Across means they are opposite of each other from the opposite side. Yeah, so that is really very easy for you to understand the geometric or the cis trans isomers. This is an example, the same example, platinum, 2 chloro on the same side, so they are cis. This is the picture, 2 ammonia on the same side, cis, and you have trans where these same ligands are across of each other. So that's not really very difficult to understand. And this is an example of an octahedral compound undergoing the geometric isomers. One is cis, where the chloro is on each other, next to each other, whereas trans, when the chloro ligands are opposite of each other. So 3 isomers, no problem. Can you recall what the 3 isomers are? First one, you have coordination isomerism. The second one, you have linkage isomerism. And these two are classified under constitutional or structural isomerism. And the third type is called the geometric isomers or the Cis Trans Isomers. And this geometric is classified under stereoisomers. And geometrical isomers have different L ligand metal ligand bond angles. Yeah, as you can see here, your ligand metal ligand bond angle in the case of cis is 90 degrees. For example, ammonia to platinum to ammonia is 90 degrees. Whereas for trans, your ammonia, platinum, and ammonia is 180 degrees. Really very easy. The common example is the Cis Trans Isomerisms that can occur in both square planar and octahedral complexes, and this is another repeat, so that's not a big problem. And this is an illustration of the Cis Trans Isomerism in octahedral compounds. So this is a cis situation. And this one on the right is the trans situation where your cis compound is pink in color, beautiful pink. And your trans compound is green in color. So simply by switching the position of the second chloro, you get a very, very different physical property. One is green in color, one is pink in color. Now have a look at these two structures down here. You have the chloro to chloro next to each other, but one is on the axial and one is on the equatorial. Now, is this compound that I am clicking at the moment, is this compound the same compound as the one at the top on the right, on the left? Are these two compounds the same? The answer is yes, they are the same because you do not have to break any bond in this compound that I'm clicking on to make it look like the second compound. You only need to rotate that molecule. You only need to bring from the left side, you bring it to the top side. No bond breaking is required to change this compound to that compound. So because there's no bond breaking happening, so you are quite safe to say that the compound at the top left is the same as this compound on the bottom left. What about this one here. You have your chloro on the back and on the back left and front right for this compound that I'm clicking. Is this compound the same as this compound at the bottom, where you have your chloro at the top and the bottom? The answer is again yes, they are the same compound. All you need to do to convert this compound on the top right to become the compound on the bottom right is to rotate the compound. No bond breaking is required. So this compound that I'm clicking at the moment is the same compound as this other compound. Yeah? So simply by rotating, you can get a different looking compound that actually is not different. So you cannot say they are different compounds. Okay? So this is still the same pink compound and this is still the same green compound. Yeah? This is another example where you have the cis 2Cl on the side, both of them. And this is the 2Cl all next to each other, but one at the top. This is the same picture. This is trans, one chloro at the top, one chloro at the bottom. This is the same trans where the chloro is on the equatorial position, one at the left front, one at the right back. But these two are the same, and these two that I'm clicking at the moment, they are the same as well. So both are cis at the top and trans at the bottom, trans isomers. Cis trans isomers in octahedral complexes. This is another example where you have dichloro. Dichloro means there are two chloro. Bis ethylene diamine, that means there are two ethylene diamine, cobalt 2. I think in your note you are given cobalt 3, but if there are no charges for this compound, so we call it cobalt 2 because we work it out that this cobalt is cobalt 2. If you are still having a problem working out that the cobalt is cobalt 2, go back to my lecture number 16. Okay? Now, the cis isomer has a purple color where your chloro and chloro is next to one another, whereas your trans isomer is green, where the chloro and the second chloro are opposite of each other. Excuse me. So these are examples of cis trans isomerism in octahedral complexes. Really easy to understand. Now, this last type of isomerism is a little bit more complex. Not too bad, but we need to be able to imagine. If I was in class at the moment, I'm going to be able to show you models, but I'm a bit limited in my explanation in terms of physical demonstration, so I'm going to try and make it up with some drawings. Now, the fourth type of isomerism is called optical isomers. Optical isomers, or called enantiomers, excuse me, let me make it longer. Yeah, enantiomers. Remember what are the cis trans isomers called? I hope you remember that they're called diastereomers. The cistrans or the geometrical isomers are called diastereomers, whereas the optical isomers are called enantiomers. They are stereoisomers of molecules or ion that are non-identical mirror images of each other. So in this discussion, you are going to be introduced to the term called handedness or chirality. You're going to be introduced to the term non-superimposable. That means they cannot be superimposed like that, yeah? And you are also going to be introduced to the term achiral or non-chiral or superimposable. So objects that have handedness, I'm going to explain to you what handedness means. Objects that have handedness are said to be chiral or non-superimposable. Objects that lack handedness are said to be achiral or superimposable. An object or compound is achiral if it has a symmetry plane cutting through the middle. So there's quite a lot of new terms here for you to understand, but they really are not difficult. Just follow me. Okay, the concept of handedness. Look at your hand. Look at both your hands. Can you see my hands? Not very pretty hands, but never mind. When you look at your left hand and your right hand, they look like the same. Yeah, they are mirror images of each other. Do you agree? They are mirror images. My left hand is a mirror image of my right hand. My left and my right hands are mirror images. However, I cannot superimpose my left hand on my right hand. If I keep my palm or tapak tangan saya facing you, they're still mirror images of each other. But keeping them facing you, I cannot superimpose them. There is no way that I'm able to superimpose my right hand over my left hand, because my little pinky is now sitting on top of my thumb of the other hand. My point finger is sitting on top of my ring finger on the other hand. The only thing that can be superimposed is this, my middle finger. Yeah. So our hands are non-superimposable mirror images. Yeah. You understand the concept of handedness? Similarly, you can imagine the same for chemicals. So let's have a look at this chemical here, where you have carbon at the in the middle, COOH functional group, R functional group, NH2 functional group, and H. This one on the left is the same. Is it the same compound as the one on the right? Is it the same compound? They are mirror images of each other. Agree with me? Do you agree with me that these two are mirror images of each other? But to determine whether they are the same compound or not, you have to rotate that compound and try to put one on top of another. If everything fits perfectly, then they are the same compound. But if even one does not fit perfectly, then they're not the same compound. So let us turn this one on the left so that carbon sits on top of carbon. Can you do that? Can you imagine? Carbon sits on top of carbon. You turn it. If you have a model, you are going to see that at least one of these will not be fitting. Yeah? Take one. You're going to see that rotating, you're going to see that I'm going to demonstrate to you on a different compound down here. For example, don't look at these images outside of the frame. Look at these images on the frame. Now, isomerism in coordination, all optical isomers, they are, enantiomers are called optical isomers. They are non-superimposable mirror images. Now, take example of this cis cobalt bis ethylene diamine dichloro. So it's dichloro bis ethylene diamine cobalt 2. So here it is. So this is your ethylene diamine. This this one here represented by a loop that is a simplified presentation of ethylene diamine. One on the left, one on the top, one at the bottom, and this chloro. If you put a mirror in front of this compound A, you are going to have compound B, correct? Where compound A is the mirror image of compound B. Do you agree with me? Compound A is mirror image of compound B. Now, to determine whether compound A and compound B are the same compounds, you cannot break any bond. You can rotate the molecule, but you cannot break any bond. If you break any bond, that means you have make it a different compound. So let us rotate compound B. So this chloro is sitting on top of that chloro. Can we do that? So we have to rotate compound B 180 degrees. So it becomes like this compound here outside of the frame. So I have managed by rotating B 180 degrees, I have managed to put my chloro at the same place as the chloro in A. But have a look at the ethylene diamine. Of course, by rotating 180 degrees on Z-axis, my nitrogen at the top is still at the top. My nitrogen at the bottom is still at the bottom. However, the nitrogen at the top connects to this nitrogen on the right back. So when this nitrogen right back is rotated 180 degrees, it becomes in this position here. It becomes left front. So without breaking any bond, this top nitrogen is bonded to the nitrogen of ethylene diamine at the left front rather than back. This is already not the same as this. And what about this nitrogen at the bottom? It is bonded to the nitrogen at the front right in compound B. So when this front right is rotated 180 degrees, it becomes this nitrogen at the left back. So this nitrogen at the bottom is connected to that nitrogen at the left back. Now compare compound C to compound A. Excuse me. When you compare compound C to compound A, you will see that the chloro and the chloro fits. This chloro in that chloro also fit. This nitrogen fitting with that nitrogen at the top. This nitrogen is fitting with this nitrogen at the bottom. However, there is a problem. This nitrogen at the left back should be connected to the nitrogen at the top. But your left back for compound C is connected to the nitrogen at the bottom. So it's very clear that compound C is not the same as compound A. So we can say that compound B is a different representation of compound C. So B is equal to C. Agree with me? We did not break any bond to convert B into C, correct? But C is not the same compound as A. Why not the same compound as A? Because the connection of these two nitrogens are different. So A is not equal to B. That means A and B are two different compounds that are non-super non-superimposable. Yeah? The two different compounds that are non-superimposable. So this is an example of an optical isomer. Yeah? This is an example of an optical isomer or an enantiomer or a chiral compound. Now, chiral means hand, sorry. In Greek, chiral is hand. So this compound is behaving like your hand. Your hands cannot be superimposed with one another. So this cis cobalt ethylene diamine chloro are chiral optical isomers and enantiomers, non-superimposable mirror images. Now let's have a look what happens when you have a trans cobalt ethylene diamine 2 chloro 2. So for trans, you have your chloro on opposite side. Having the mirror image gives you this. So let's say this as let me see. So your two images here, if this is C and that is D, so C is the mirror image of D. So let us determine if C is equal to D or if C is the same compound as D. So what do we have to do to convert C into D? You will just have to rotate this compound by 90 degrees because you want to put this chloro to that position. So rotating this compound clockwise to 90 degrees, you are going to produce your chloro on the same side. Do you have the same side ethylene diamine? Yes, of course, because the top nitrogen and bottom nitrogen are still the same, and the top nitrogen is connected to the same nitrogen here. So rotating this compound by 90 degrees without breaking any bond, you can reproduce the compound exactly. This compound, what do I say? C, D, D, A. Yeah? Just 1 second. Let me label them so you don't get. Yes, I have labeled this compound D, that compound E, where D is a mirror image of E. Agree with me? And when I rotate E 90 degrees, I get F. Do you agree with me? I'm rotating E 90 degrees clockwise, I get F without breaking any bond. Is F the same as D? Yes, it is, isn't it? So because F is the same as D, that means E is the same as D. So D is mirror image of E, and D is superimposable. You can superimpose D with E. So your trans CO ethylene diamine Cl2, they are superimposable. They are not optical isomers. They are not enantiomers, and their behavior is called achiral. Achiral as opposed to chiral, not hand. This is hand. This is not hand. So the trans isomer of, this compound is not optical isomer, whereas the cis compound or cis isomer is also optical isomer. So you get me? I hope you understand that. So repeat. When you have a cis of cobalt 2 ethylene diamine chloro, you are going to see that it is a chiral molecule because the two mirror images are not the same compounds. They are not superimposable. But the trans On the other hand, after we do the same operation, you will see that the two mirror images are the same compound. They are indeed superimposable, so they are achiral. So this one is not optical isomers. These are optical isomers. The cis optical, the trans not optical. So to see whether you understand optical isomerism, there is a question. Draw all stereoisomers. So what are stereoisomers? Stereoisomers are either geometric isomers, which are cistrans. So you have to determine whether the cistrans isomers exist or not for compound A and compound B. And number two, you also have to see the second type of stereoisomerism, which is optical isomerism. Do they have the superimposable mirror images, or don't they have superimposable mirror images? So the compound A that you have to look at is platinum, 2 ammonia, 2 bromo, and compound B that you have to look at is chromium with 3 ethylene diamine. So the plan is determine the geometry around each metal ion and the nature of the ligand. Place the ligand in as many positions as possible. First of all, look for cis isomerism. If they exist, then determine if they are optical isomers. So the question number one is really quite easy. Really, you can see right away that compound A has cis and trans isomers. So they exist geometric isomers. This is your trans isomer of the compound, and this is your cis isomer of the compound. But when you try to see whether your trans has optical isomers, all you have to do is look at the mirror images. Oh, can't see it here. Oh, it's not here. It's very easy for you to see. So I would like you to try and draw the mirror images of these trans and rotate. See if you can get the same compound. If you get the same compound, so they are not optical isomers. Similarly with your cis isomer. If you draw the mirror images of the cis isomer and simply by rotating, you can convert one mirror image to another, so they are also not optically active. So when you do that, you are going to see that the mirror images of both the trans and the cis are superimposable. So this compound is it only has geometrical isomerism. They don't have optical isomerism. Yep. For question B, maybe the story can be a little bit different. You have chromium in the middle and 3 ethylene diamine ligands surrounding it. So let's have a look. So you have chromium with 3 ethylene diamine, one on the right, one at the top, one at the bottom. Now, can you see that you will not have cis trans isomerism here? You do not have cis trans because they are all identical. Since all the ligands are identical, you don't get geometric isomerism, i.e. no cis trans isomers. But if you look at this compound and you draw a mirror image of it, which is here, so we call this A, we call that B. When you flip B, you are going to find that this C is not the same as A. So A and B are not the same compounds. They are not superimposable. So they are optical isomers. So in chromium 3 ethylene diamine, you are going to find that geometric isomerism doesn't exist, but optical isomerism does exist. The mirror images, are two different compounds. They are non-superimposable, so therefore they are optical isomers. And optical isomers are chiral molecules. Chiral molecules behave like a hand. Remember this? Oh no, not yet. Yeah, I will show you. Yeah, this one here. Optical isomers are non-identical. Objects that have handedness are chiral. Object that doesn't have handedness are achiral, non-superimposable. And an object that is chiral has symmetry plane cutting through it. Okay, now what's this all about? When we talk about optical isomers, as you can see, we already work out in the previous slide that these do not have geometric isomers, but they have optical isomers where the mirror images are non-superimposable, so they are optically active, they are chiral compounds, and this is the picture of them. Yeah, this is how ethylene diamine is arranged. 3 ethylene diamine ligands are arranged around a metal center. You will see that after going through the operations that these are chiral molecule. But if you have a metal, cobalt for example, with 6 ammonia molecules bonded to it, you are going to see that this compound does not have any isomerism. It does not have any geometrical isomerism. It does not have any optical isomerism. Why? Because when you put a mirror image of this compound, you are going to exactly be able to see that the mirror images are the same. You can superimpose them. So this cobalt NH36 are achiral, whereas this cobalt 3 ethylene diamine is chiral. Enantiomers, so when you have chiral molecules, when you have optically active compound or optical isomers, you call them enantiomers. Now, enantiomers have identical properties except for their reaction with other chiral substances and their effect on plane polarized light. So what is a plane polarized light? Let me jump through this one. Now, when you have a light source here, this is a bulb, and you pass the light through a polarizer, polarizer will only allow light of the same orientation to pass through. It will filter out any other lights that does not have that same orientation wave. So the polarizer, if your polarizer is a vertical polarizer, only vertical waves will pass through, and those vertical waves are called plane polarized light. Now, when plane polarized light pass through a solution of compound that is optically active, a solution of compound that has non-superimposable mirror images, those compounds can affect your plane polarized light in a way that it can rotate the orientation or direction of your light. So a rotation of the plane polarized light will occur when it passes through an optically active compound. So what is seen by your eyes here after this plane polarized light, vertical plane polarized light pass through your optically active compound, what you will see is some kind of rotation. You will observe some kind of rotation. The light will become rotated. So that is what's called the effect of chiral compounds on plane polarized light. Chiral compounds can rotate the direction of plane polarized light either to the right or to the left. Therefore, they are said to be optically active. Yeah, and this effect can be measured with a polarimeter. There is a machine or there is an instrument in the lab which is called a polarimeter that is used to determine chirality of any compound. not only coordination compound, any organic compound that has chirality can be measured using polarimeter. So this is how they are measured. Chiral molecules, they are optically active. They can rotate the direction of plane polarized light, whereas non-chiral molecules are optically inactive. They cannot rotate the direction of plane polarized light. So plane polarized light is obtained by passing ordinary light through a polarizing filter, as you remember the vertical. In a polarimeter, the plane polarized light is passed through a chiral solution and the polarization plane measured with an analyzing filter. If you see that the light is rotated to the right, you say that that compound in this solution here, you say it is the dextro-rotary isomer. But if the plane of light is rotated to the left, it is called a levorotary. Dextro-rotary is given a plus sign, whereas a levorotary is given a minus sign. Dextro means right. Levo means left. So dextro-rotary rotates to the right, levorotary rotates to the left. Now, remember, this is the same slide that you've seen before. If there is the same amount of dextro-rotary and levorotary isomers in a mixture. So, for example, if you put 1 mole of dextro-rotary in that solution and 1 mole of levorotary in that solution, what happens is both will be working at the same strength. The rotation to the right by the dextro-rotary will be cancelled exactly by the same amount on the action of the levorotary to the left. So dextro-rotary rotates it to the right by this much, and because there is the same amount of levorotary, it is going to be rotated back to its original position. So the rotation to the right is cancelled exactly the same amount by the rotation to the left. So it seems that the plane polarized light does not undergo any rotation. So when you see that that solution does not rotate the plane polarized light, there are 2 possibilities. The one possibility is that your compound is achiral or non-chiral. The second possibility is your compound is chiral, but the dextro and the levo, they exist in the same amount. So the effect of one is cancelled by the other. So when that mixture happens, it is called a racemic mixture. Racemic mixture is when your dextro-rotary is as much as your levorotary, where the net effect of the plane polarized light is 0 rotation. So that about wraps up my lecture, my last lecture. So for some exercise, I would like you to determine for these compounds A, B, and C, platinum 5 water, bromosulfate, chromium 5 ammonia nitro, chromium ethylene diamine 2 ammonia, I would like you to state what type of isomerism can be observed by on each of these 3 compounds and draw the structures. So remember, there are 4 different types of isomerism that are categorized into 2 broad. The first one, okay, let's go back. Let's go back to the first slide. Yep. The first one is constitutional isomerism divided into 2. One is coordination isomers, and the second is linkage isomers. The second broad type is stereoisomerism. One is geometric isomers, one is optical isomers. Only 4 types. So determine based on what you have understood in my lecture today, determine which of these compounds have what kind of isomerism. So, all the best, people. I have concluded all my lectures, all 17 of them. I'm going to be giving you some exercises, and I hope you are going to be able to do those exercises, practice on them, show me your answers in our discussions. And I hope with that preparation and many, many exercises, you are going to be able to tackle your test 2, which is in 1 week time, and your final test, which will be in about 2 weeks time or 3 weeks time. So all the best, people. I hope you have understood all of my lectures, the 17 of them for this semester. And I hope you are doing well, you are keeping yourself motivated, and I hope you will get A for my subject. Bye-bye. Assalamu alaikum. See you in our live discussion.